So hi there, again. This is Obi-Wan Pesper and Simplex Pachinko. Apologies if anyone was actually here for a bit. Apparently my video encoder was overloaded and then my entire computer needed a restart. So, I think the moral of this story is make sure that your graphics driver updates have actually completed updating before you actually do anything with it, because I'm pretty sure that's what happened, is that it just decided that it was not entirely updated yet and just stopped working right. So, do be careful out there. Alright, so, as I said in previous incarnations of this stream, my plan for tonight is to showcase the final exam that I wrote for pre-calculus, give some ideas as to the kinds of questions that I asked and why I asked them, and then to help out any educators out there who might be in a similar situation, like what is it that you're looking for to try to create, as well as give students the opportunity to look at the kinds of questions I'm asking and maybe make some inferences as far as what their teachers might ask on their final exams. That's not to say that my way of doing things is the end-all be-all. Quite the opposite. I am only one of many, many teachers at this particular institution, and not even all of us agree on what should be on the final exam. So this is more or less just for, what I choose to do. Okay, so my final exam has a total of 12 questions. They range in point values from 4 to about 8. Yep, from 4 to 8 points. They need to cover the very, very large amount of material that we have in pre-calculus, and this is only a one-semester course, so it kind of comes through very quickly, and a lot of students feel like they're very overwhelmed by the amount of material we have. It happens. So, I'm going to start out at the beginning because it's a very good place to start. So, question 1. Not again. Come on now. Alright, question 1. Oh, come on. 4p squared plus 34 is equal to 12p. Okay, so this is a standard quadratic question, which, again, many students have received quadratics that are nearly identical to this. You may see a quadratic with any number of answers. So, as we know, quadratic equations come in 3 basic varieties. You have your kind that have 0 solutions. You have your kind with 2 solutions. And you have your kind with 1 solution. These are, again, what you would get if you have the quadratic equation ax squared plus bx plus c is equal to 0. Let's make sure that you can actually see that. So, when you have ax squared plus bx plus c equals 0, you're looking for these zeros or the solutions to the equation. So these zeros of the polynomial end up being places where this crosses the x-axis. The direction in particular doesn't really matter because whether it's going up or it's coming down, it's going to be the same thing. So whether this is going up this way or down this way, it was all still good. So looking for a solution to a quadratic equation, you could try factoring, you could do all sorts of other stuff, but the first thing you want to do here is to move this term to the left so that you get all of the terms on one side. So subtract 12p from both sides. Get a 4p squared minus 12p plus 34 equals 0. I do see a lot of students attempt to solve this equation just as it sits right here. So one of the ways in which a student might not get this correct is to say, okay, I'm going to factor out a 2 from the left side and make it 2p squared plus 17 is equal to 12p. Or alternatively, they'll turn this into a 4p squared minus 12p equals negative 34, and then say that this is going to be 4p times a p minus 3 is equal to negative 34, and then say, okay, now I'm going to solve this. Alright, well, if you're going to try to solve this, you're looking for two factors of 34, negative 34 even, that are going to, like this one is 4 times some value, and this is 3 minus that particular value. So how are you going to figure this out? And so they usually flail for a while and then just can't do it. So my point here is, this doesn't work. You cannot do this. So don't try and mess around with trying to factor stuff on either side. This is, generally speaking, how you could potentially do this, but the problem is that you're going to end up with a really hard time just generally trying to figure out what the solutions are. So you really need to get it into your standard form for quadratics, equal to 0. Everything else is on the other side. Then what do you do with this? Well, this is our quadratic formula that we're looking at. Again, keep it in the right order. So your x squared, or in this case p squared, is going to be first, your x term is going to be second, and your constant term is going to be last. So what do we do with this? This is called quadratic formula, so p is going to be equal to, in this case it's p, not x, negative b plus or minus square root b squared minus 4ac all over 2a. This is a negative 12 plus or minus square root of parentheses negative 12 squared minus 4 times a is 4, c is 34. Divided by 2 times 4. So p is equal to a positive 12 plus or minus the square root of 144. This is going to be a plus 16 times 34. I could do it in my head and all that, but oh no, sorry, that's a minus. There's only one negative in there, so it's a minus 544. Divided by 8. P equals 12 plus or minus the square root of a negative 400 divided by 8. 12 plus or minus. Here, this is the same as the square root of 400 times negative 1. I am going through this rather slowly, step by step, so you can see it. P is equal to 12 plus or minus the square root of 400 times the square root of negative 1 all over 8. Square root of 400 is 20. This is 12 plus or minus 20. The square root of -1 is abbreviated I, or depending on your field, engineers, physicists might call it J, all sorts of other stuff like that. It's all cool. But either way, this is the very poorly named imaginary term, or imaginary number. So the square root of -1 is just defined as I, which is this so-called imaginary term. The rest of it is the real term, the 12. And then here, this is all divided by 8. So we can factor out, either you can factor out common factors up top, or you can divide individually and see what you can get out of either of them. In this particular case, you can factor out a common 4 from the top, leaving 3 plus or minus 5i divided by 4 by 2. Your 4's can divide out. This leaves us with 3 plus or minus 5i, all divided by 2, is equal to our p value. I am perfectly happy leaving it like this. There are other people who want you to specifically separate this out, so you would be thinking this is 3/2 plus or minus 5/2 times I. Alright, that would be the slightly more expanded version of doing this. Now, why did I ask this question? So I have many different questions at my disposal. I could have just asked any quadratic, for that matter. I could have done one with one solution. I could have done one with two solutions. However, later on we will be seeing more quadratic equations that have either one or two solutions. So I felt like this was the best time to ask something where it had 0 solutions, and specifically, since our class deals with complex numbers, have a complex solution. So I very specifically wanted to ask one where we had a complex solution. All right. Question number 2. Solve the triangle. Capital A is 42 degrees. Lowercase a is 12 centimeters. Lowercase b is 17 centimeters. For the question, solve the triangle, what I'm really looking for is that we have all A, B, and C, both angles and side lengths, as found. So A is given as 42 degrees, lowercase a is given as 12 centimeters. Side B is given as 17 centimeters. That's all the information we have. So, for this, what we need to do is, first of all, draw a diagram. Actually, you know what? Let's keep that ink. And it doesn't have to be any particular kind of diagram by itself. You should not infer anything from the diagram as it's drawn. So, labeling A, B, and C somewhat arbitrarily. This is going to be 42 degrees. A, side length, is opposite. Its corresponding angle. So little a here is the opposite side to angle A, big A, down here. 42 degrees is corresponding with 12 centimeters. B, down here, is 17 centimeters, corresponding with an unknown angle B, and unknown angle C corresponding with little side C. Okay. So for this, we want to be able to solve what this triangle is. What are all the side lengths and what are all of the angles? We don't know anything about side or angle C, and we know that angle B must be opposite our 17 centimeter side length. So, for students, here, the immediate thought is, well, what do I need to do in order to figure out what these angles are? and what these side lengths are. For this, you need to look at the fact that we don't have any information about what kind of triangle we have here. Yes, this might look like a right triangle, but you can't trust that. Don't trust the diagram unless there is an actual right angle in there, in which case you would be able to put, okay, that's 90 degrees. But in this case, it is not 90 degrees. We don't have any information about that. So, we have to assume that both B and C are not going to be right angles. What we're going to do is we're going to say, well, based on what we learned in class, for any non-right triangles, we may use the law of sines and or law of cosines. Now it's up to you which one you want to do. It doesn't really matter. You will find answers to this particular problem through either method. In order to do law of sines, you must have, and we've done this before in this channel, so you must have one corresponding pair an angle and a side lost my cursor. There we go. Okay, so you must have one angle and one side plus one more piece of information. Doesn't matter what kind of piece of information it is, just as long as you have some information about either a side or an angle. You need one more piece of information, and then you can solve everything using law of sines. Using law of cosines, you must have at least two sides plus one more piece of information. Now, why is that the case? Well, for law of sines, what we have is that the sine of A over A is equal to the sine of B over B is equal to the sine of C over C. You can use any of these that you would like to figure out. In the case of what we have here, we have the corresponding sides, A the angle to A the side. So we can do the sine of 42 degrees divided by 12 is going to be equal to the sine of B divided by 17. We have no information about C, so we're just going to leave that off entirely. When we do this, we're going to solve for the sine of B, so we're going to multiply both sides by 17. So 17 times the sine of 42 degrees divided by 12 is going to be equal to the sine of B. All right, and B is equal to, in this case, the inverse sine of 17 sine of 42 degrees divided by 12. Which, as long as your calculator is in the right mode, you are going to get inverse sine of 17 over 12 multiplied by sine of 42 degrees. You're going to get the value of 71.42995302224 degrees. Do you need that precision? No, it's not going to matter. But you do need to have this stored into your calculator so that you will be able to keep the exact value as far out as you can go. You don't need to write it, but you do need to store the exact value. On a TI calculator, there's this nice little button way down here called STO, or store. When you hit that, it will allow you to store whatever number you just plugged in, or whatever expression you just plugged in. It'll evaluate it and then plug the answer to that expression into whatever variable you just marked. So generally speaking, I do that as whatever letter you need for the law of sines. So in this case, B. Now there's also another weird thing that's going on here. The sine of B is equal to this stuff. Now all of this stuff has a particular value of 0.9479350 and more stuff after that. Now what this means is that on the unit circle, horribly drawn I know, the sine value represents the y value or the vertical value of that particular angle. So this is roughly 95% the way from 0 up to 1. So where is that? Well, that's like here-ish. And the sine of B represents the vertical value, so that's y values. So on a unit circle, r is equal to 1. And the sine of B is equal to y over r, or just y on the unit circle. So if the sine of B is equal to 0.9479, etc., then this means that it has a y value of that. Y equals 0.947935, etc. Which means that it struck the circle here, and it strikes the circle here, ish, right? I'm not a good artist about this, but it's close enough. Which means the angles that we care about are these two. One we've already found. This is approximately 71.43 degrees. And then what's this one? So this angle here. So that angle here, which is obtuse, is potentially what B is up here. It could be an acute angle, but it could be an obtuse angle. We don't know. So we have to account for the one that is obtuse, just in case it does actually work. So the way to do this is you say, well, the sine function allows for the supplementary angle over here to also be 71.43 degrees, give or take, again. So if that's the supplementary angle, then that means that the secondary angle on this side, the obtuse angle, is going to be 180 minus that. So this is actually just B1. B2 is going to be equal to, this is 180 degrees minus the inverse sine of 17 sine of 42 degrees over 12. And in doing so, B2 will be approximately equal to 180 minus that B that we found is 108.57 degrees. Again, very approximately, because of the zeros here, because of the nines here, this is why we get zeros down over on the other side. So now we have two different cases. We have one triangle that looks like this. Nope, 71. We have a 42-degree angle here. We have a 71.43-degree angle here for B1. That's A. So now we need to find the value of the angle for C1. Well, this is going to be 180 degrees minus parentheses 42 degrees plus our 71.43 degrees. Right. Again, this is 429953, etc. But we can just shortcut it as this, as long as we don't actually type in, or as long as we don't start using 71.43 in calculations. So that is something you should not do. Okay, so this is going to be 42 plus B, and then we're going to subtract from 180, and it comes out with a value of C1 is equal to this, which is very approximately 66.57 degrees. And again, 5700469776. I'm going to store that value to C in my calculator. Alright, so now I get, again, there are two different possible triangles that you can create. So, C1, we end up with, alright, let's do B1, C1, little c1 like this. We end up with 71.43 degrees. C1 is 66.57 degrees. And now to get little c1, we need to plug this back into the law of sines using the sine of A over A that we already found. Don't use sine B over B, even though it's tempting. You can do it. It's perfectly legal. It's just that if you screwed up somehow in finding big B, then that error will carry over. If you also rounded this, your error will carry over. So my recommendation is go back to the beginning. You look at just the stuff that you were given, and then the new information on top of that. So you will be closer. If you screwed up B, you've also screwed up C. All right. But you'll be closer if you start with A and use this than if you use B from here. Also, this formula does not need to be written in this particular order. You can, in fact, invert the entire formula. So A over sine of A can be equal to C over sine of C. What we're going to be looking for here is this little c value. So how do we solve for that? We'll just multiply by the sine of big C on both sides. Over here we divide, it becomes 1. Over here I could have done this earlier. This gets us little c is equal to the sine of 66.5700, etc. degrees times A was, where'd it go? 12? Yeah. Times 12 divided by the sine of 42 degrees. And little c from this is going to be, again, approximately equal to, this is the sine of C times 12 divided by the sine of 42 degrees. We get an answer here of 16.4550275, etc. centimeters. This is not likely going to go beyond 1 or maybe 2 decimal places. So it kind of depends on what your instructor's looking for. I would say that this is probably close enough to 16.5 centimeters. We're good with that. If you need to, it can be 4.6. So, again, it all depends on your instructor. Make sure you read the question. So with this C1, this applies to all of them, not just C1, but this particular setup applies to C1 only. Okay. 16.5 centimeters. Probably close enough for what we're doing. Alright, now we've got the alternate set. Rump. Didn't actually get to the law of cosines yet. It's alright. Alright, if B2 is obtuse, then what we've got is this same 42-degree angle here, but now B2 is going to be an obtuse angle, 108. So it goes out this far, for this being still 12 centimeters. That's totally 12 centimeters. Not to scale. Alright, so this is still 42 degrees. This is now going to be 108.57 degrees. Alright, so then we're looking for C2 and little c2. So how do we get those? Well, again, same deal as we did before. We have to look for C2, big C2, is equal to 180 degrees minus the sum of the angles we already have. So again, 42 and 108.57 degrees. Which is going to be approximately. I need to go back and redo. This is 180 minus B. I'm going to store into the letter beneath B on my calculator is G. So my B2 is going to be second row B. It's just something I do to keep myself organized. So now 180 minus parentheses 42 plus G is going to get us a C2 value of 29.43 degrees. Again, 429953, etc. So this is what we're getting for C2. So then little c2 is going to be found again, much the same way that we did little c1. Little c2 over big C, sine of big C2 is going to be equal to, again, a over sine of big A. We need to find little c2, so multiply both sides by sine of c2. So c2 is equal to little a was 12 times sine of big C2 was 29.43 degrees. Again, not that value, but really close to it. Divided by the sine of 42 degrees. So this is going to be 12 times the sine of, I stored this into the second row C, so that is H on my calculator, divided by the sine of 42 degrees is going to be equal to, little c2 is equal to approximately, 8.811896 centimeters. And again, more after that, but I don't really care about this. I only care about the first, maybe second decimal place. So 8.8 centimeters is going to be approximately our value. That's going to be good enough for now. So this means our A, B2, that's in the way, I'm in the way. A, B2, C2, we've got 42 degrees here. B2 was again 108.57 degrees. C was 29.43 degrees. Little a was 12 centimeters. Little b was 17 centimeters. And little c2 was 8.8 centimeters. So here's our second triangle with the obtuse angle. This was me trying to get through this and try to explain everything, so it did take a little bit longer than normal. However, I'm expecting students to spend a good 10 minutes on this. So if they're working quickly and efficiently, 10 minutes is about as much as they need. It will be roughly, or I gave it 8 points. If a student figured out only the one triangle up here, they got half credit. So it was usually either a 4 or 5, depending on how their work was. Again, it kind of depends. You could tell where the break point is. If the student knows exactly what they're doing and they solve for just the first triangle, then yeah, I'll probably give them a 5 out of 8. But if they're just doing the half and it's like kind of struggling through, not really understanding what's going on, they might deserve a 4. One of the reasons that I also enjoy using law of cosines for this is that A, it gives you the fact that there's 2 answers up front, and B, you will find both of them immediately. So for a law of cosines, what we're looking at here is you have to be able to pull the angle here and say that we're trying to solve for this side here. So this is, for this particular one, a squared equals b squared plus c squared minus 2bc cosine capital A. Now the students in my class had a one side of a sheet of paper. They could write anything that they wanted on it. So I'm expecting that they will have law of sines and law of cosines in whatever forms they need. And you know, I told my students, for efficiency's sake, don't worry about trying to make this like every single law of cosines and do all 3 of them. You could just know that this is the Pythagorean theorem. But it's generalized with this other stuff here. So whatever terms are here, B and C, are going to end up in the product of that other part. So as long as they sort of know what they're doing, they don't need the whole thing. They don't need all 3 forms. Okay, for this, what we're going to get is that we had A, which was 12. We had B, which was 17, and we did not have C, so c squared. Minus 2, B is 17, C is just C, times the cosine of 42 degrees. And happy belated towel day to everybody. Get yourself some Pan-Galactic Gargle Blaster, and make sure you have some salty protein snacks just in case. So, we have here 12 squared is 144, 17 squared is, nuts. Let's see, 225, 289, plus c squared minus 34 cosine of 42 degrees times c. Alright, I'm going to subtract 144 from both sides. Oh, look, it's a quadratic. And guess what? It's got two solutions. It's got two real solutions, and these will come out to be, triangles that we can actually use for this. So this is 0 equals c squared minus 34 cosine of 42 degrees plus, times c, plus 289 minus 144 is going to be a 145. This yields the answers for C. 2b, you guessed it. Well, we'll plug them into my quadratic formula here. This is going to be 1 for A negative 34 cosine 42 degrees for B, and a 145 for C. This yields us C values of 8.8118965, etc., and 16.455027, etc. I couldn't actually see it on my calculator because my program ends the program, and unfortunately. Alright, so C could be either 8.8118965 or 16.455027, etc. And guess what? We know what those values were, right? We got those at the end last time down here. But now we've got them at the beginning in the law of cosines. So that means if we use the law of cosines, we already know that there are two different valid triangles, or at least they seem valid. And so our next step will be to figure out where these are and get the other items for them. So we'll call this one C1 and this one C2 because, oh, look at that. Oh, no, it's backwards. We'll call this one C2 and this one C1 just cuz. Hang on one sec. So then from this perspective, we're finding these C values first, and then what do we do with them? Well, we're going to plug these back into the law of sines again. At least that's the way I'm doing it. You could, in theory, plug them back into the law of cosines again, and this time go for the cosine of B and or cosine of C values that you want to get. That's fine. It works just the same as what you need for all this stuff. So my recommendation is that when you have this, you know that you've got right. So you need to find the C value for each of these. Yeah, alright. Doesn't much matter. If you go for the sine of A over A equals the sine of C over C. Again, here this is going to be sine of C is equal to C sine A over A. So the sine of C is going to be equal to 8.8. That is a C2. 8.8, etc. Sine of 42 degrees over 12. In this particular case, you know that our little C1 value here is smaller than A1, or A, our A value. Therefore, our angle C2 must be smaller than angle A. So when you do this, you get the sine, nope, you get that C2 is going to be equal to the inverse sine of 8.8 sine of 42 degrees over 12, and that this value must be smaller than 42, because we already had that. Okay. All right. Nope. That is the sine inverse arc sine. Apologies. So, arc sine of 8.8118965, etc. times the sine of 42 degrees divided by 12 is going to be 29. Big C2 is 29.43 degrees. Again, this is really an approximation, not actually equal to, but whatever, it's close enough. So then this means that B2 must be equal to 180 degrees minus the sum of 42 and 29.43 degrees, which again gets you that value of 70. Nope. Sorry, B2. We found down here. It's that same value, 108, just right there. 108.57 degrees. Hey Matthew, doing all right? How are you? Now that I've got my computer a little bit sorted out, it's going much better. I ended up missing about 20 minutes of the stream because my computer just got like crushed. Yeah, I mean, this is all kind of, in theory it's one problem, but I'm solving it two different ways, so I'm kind of showcasing both pieces. So using law of cosines, for instance, solving this particular triangle ends up being a little bit easier-ish, as long as you keep track of what you're doing. And again, the other problem with it was that there are two distinct answers for this particular triangle. So it is kind of a mean thing to do sometimes. Yeah. So this one really only takes, you know, a small amount if you know what you're doing. Which I mean, I'm intentionally expanding this out a bit so that people can see what I'm doing. But if I did all the work in my calculator and then just wrote down a single line, yeah, it could take about, you know, this much. Be just done with it here. All right, yeah, so this is my actual final exam that I set last week. So all of my students took this last Wednesday. This is why I took the day off last Wednesday. And then subsequently took Friday off as well because I was just swamped trying to get stuff done. Finally got final exams done on Sunday. Got all the grades in on Sunday, and everybody got their reports on Monday. So, you Yeah, Sunday night I was like, all right, screw it, I'm playing Elite Dangerous. They were to be expected. Generally speaking, they were across the board, right? I've got students who are up in the A's and students who are in the F's, but everything was expected exactly where, not exactly, but approximately where I thought it was going to be, maybe minus a few points here and there. How appropriate. Thank you, Pretzel Rocks. Yeah, so we had two options here. Either you take law of sines and you go for this stuff, or you could go law of cosines. I also recommend strategically that if you're trying to solve for the bigger angle, go for the law of cosines. So in this particular case, we want the cosine of, we want c1 squared is equal to a squared plus b squared minus 2ab cosine c1 like that. So I'm just going to throw this all in. This is 16.455, etc. Squared is equal to a squared. A was 12 squared plus b is 17 squared minus 2. A was 12, b was 17 times cosine of c1. We're solving for c1, so move this over, move that over. 2417 is going to be 408 cosine c1 is equal to, this is a 144 plus 289 minus the 16.7, etc. It's going to be 270.7679, more stuff after that. 44 plus 289 minus answer. It's going to be 162.232 and more stuff. Divide by 408 is going to get you the cosine of C1. And then C1 is going to be equal to the inverse cosine of that stuff. 162, etc. over 408 is very approximately 0.397627. Now this could be off by a little bit because I did round in my calculator. I know. But the inverse cosine of that particular angle, C1, is going to be approximately a 66.5700 degrees, and then beyond that. So what we cared about in the first place was this was going to get us a 66.57 degrees, and then beyond that we don't really care about the rest of the decimal places. It's accurate enough. All right, now it's important to note that what we were looking for the secondary answers every time we had a sine. So here, why don't we look for secondary answers when we have cosine? Well, that's because the secondary answers, cosine values, are x over r, which on the unit circle, cosines are just equal to the x values. So then when we draw this in, we had a cosine value of about 0.4, so that's just under half, that's like here. And it's x value, so it's x equals 0.4. Again, give or take. So where does that put us? Well, that puts us here, and that puts us here. So this angle here is our 66 degrees, 66.57 degrees, and this angle here is not. All right, if you look at this, this is 300 and something degrees, or very nearly 300. Yeah, not quite. It's a very large number. So that's not really going to work for us. It's 293, right? 293 degrees inside of a triangle? Yeah, I don't think so. So here, C1 could have been equal to 293 point something degrees, and we just say, yeah, that's not happening. So C1 gets us this value here. And again, the reason that I'm doing this, when you're solving for bigger angles, use cosine, because there's only one possible way that you can, or one possible number that you can find. That's it. You're not going to get anything else. And in fact, I should have recognized this. Right, this is 16.4 centimeters. It's already less than our 17 up here, so we didn't need to use law of cosines. We could only get angles that are less than 71.43 degrees. So, oh well. Or rather, we don't know what B is for that from that perspective. So we'd say, okay, we got 16.5, that's less than 17, therefore B1 must be the biggest angle. Would have been done with it there. And we could just use law of sines for all of it. So again, for smaller angles, use law of sines. All right. Got anything you want to talk about, Matthew? I'm always game. For teachers, the reason that I'm looking at this is we're doing law of sines, law of cosines. It gives me some insight as to how the students will go about the individual problem and solve, and what their strengths and weaknesses are within this entire setup. It is worth another 8 points. Yeah, right. I said that before. Yeah, so generally speaking, you're talking about finding the somethingth root of this thing. So the square root, cube root, fourth root, fifth root, etc. There might be other particular names for it, but I don't necessarily know them. But yeah, I would generally just call them, some number root. X to the 6 equals, I don't know, 500, right? And we're looking for x equals 6th root of 500. This is actually something I'm doing later. So if you want the principal root, then this is just going to be what number, when we multiply it 6 times, gets us to 500. This is going to be the, let's say, 500 raised to the 1/6 power is going to be 2.81726911385. All that stuff. So this is the principal root. That doesn't mean that that's the only answer. The easy one is going to be called the secondary, which is going to be, in this case, the negative of that. because it's an even root, we're going to get the positive and the negative answers to be exactly the same. But then there are tertiary through whatever the name for sixth least important is. Um, so principal root is going to be the primary answer that you find every single time that you're looking for it. So in this case, principal root means what are we doing notationally when we just write the something root of a number? So like, what's your calculator going to find, right? So when I type in the sixth root of 500, it spits out this answer. That's the principal root. So 2.8179269, etc. The secondary root is visible on a graphing calculator. So, you know, we get something like this. X to the sixth equals 500. Well, how do you graph that? It's going to be like this, that. Here's y equals 500. Here's y equals x to the sixth. And then you've got these two solutions here. And also, note the spelling here. I do it all the time, so don't feel bad. I keep having to check, like, every semester. So principal meaning most important, as opposed to principal meaning, like, good versus bad. I mean, maybe, but at the same time, so you could argue that there's plenty of physical meaning. You just have to find it. So in terms of like real life scenarios, what you've generally got is so the pattern that's going on here. Pattern for just like y equals the square root of x is yeah. No, I understand that. So operations, I can say what they do. So here, right, this is similar to what's going on with just y equals x squared. But these are going to be inverses of each other. If you look at the pattern between all of the numbers in your quadratic, so like just x and x squared, then you've got this -3, -2, -1, 0, 1, 2, 3. On the other side, you've got 9, 4, 1, 0, 1, 4, 9. All of these end up being +1 going all the way down. Over on this side, though, what you've got is 9 to 4 is a -5. 4 to 1 is a -3. 1 to 0 is a -1. 0 to 1 is a +1. 1 to 4 is a +3. 4 to 9 is a +5. So in this particular case, you're looking at the pattern that's going on here is unlike a linear function, which is continually adding the same number over and over and over again to your outputs. Or to look from one output to the next, you're adding a constant value. For quadratics, you are adding a linear value to each of these things. So our amount that we're adding is now linear. So it itself is increasing by a constant amount. So this is +2, +2, +2, +2. So if we're looking at this, this is our change in y, and this is the change in y, which comes in handy later with calculus, but we don't have to worry about that. In the square root functions, I think I understand what you're saying, is that basically you're describing it in reverse, which is kind of the exact same way we're talking about this here. Like, right, you're explaining it in reverse, essentially. So it is kind of just an inverse of the uh, power functions. It is itself and like its own power. So the inverse here is a 1/2 power, and some of that you can see if you explore like just typing in like x to the n and then coming up with different values for n. And I don't mean n like a particular number, but y equals x to the like m over n. Just make it any rational number. Figure out what patterns exist here. So if they're odds or evens or negatives or positives, or m is bigger or n is bigger, then you start seeing interesting patterns that exist. And like change the numbers around so that they do all kinds of crazy stuff. So not exactly, but it doesn't 100%, cleanly invert. But here's the thing. If you were to just look at this one, what we're doing is we're saying that here's our x, here's our root x. Well, these numbers are going to be our... can't do that. 0, 1, 4, 9, 16. Is that even? Yeah, it's off. And over here, our square roots are going to be 0, 1, 2, 3. What's happening is that our x values are now increasing by that linear amount. So this is our +1, +3, +5, +7 on the next one, even though you can't see it. Right, 16. And then here on this side, we've got our +1 every time. So one of the famous examples of how do square roots actually play out in the real world is when you're talking about like stopping distance. I curse myself for not having this actually out, but oh well. I wasn't planning on going here, I guess. So your speed... No, other way. Versus your stopping distance ends up as a square root function. At least I think I have that backward. Or I think I have that the right way around. So as you start going faster and faster, your stopping distance keeps increasing. Speed increases at a... I'm going to have to look it up now. Okay, so stopping distance is going to be equal to 10 squared plus 3v over 10. That doesn't quite. Nuts. Yeah, so I might have it backward. Boo. No, I don't want that. Yeah, alright. So yeah, this would be minus d on the other side, and you'd have to solve a quadratic, of course. Anyway. Yeah, I mean, clearly that makes sense, right? Zero speed, zero distance. Yeah, so it has to do with some other bits that are in the constants, but basically your v over 10 can be your variable for it, rather than having it be just v over 100, and then over here 3v over 10. You can incorporate the 10 as part of your variable term, which then simplifies things a bit when you do all this out. I mean, hell, why not? So a squared plus 3a minus d. Then a would be equal to negative b plus or minus square root 3, right, 3 squared is 9 minus 4 times 1 times negative d over 2. 3 halves plus or minus square root of 9 plus 4d over 2. Right, so that's the simplified version of this formula. Your a here, your velocity would be equal to then 10 times all of that. So negative 3 halves plus or minus square root 9 plus 4d over 2. And I'm guessing we probably just want the positive answer. So it's going to be 5, negative 15. That's interesting. Plus 5 square root 9 plus 4d. So that's interesting. I'm going to hold back on analyzing this much further, but so it is a physics equation. Which one's concave down? No, this, yeah, I'm wrong with this one entirely. So that was wrong. This was it here, so your velocity versus your stopping distance here. It's going to be that way. So that makes much more sense. And actually, this is not going to go through 0, 0, so there is a physical... Oh no, it doesn't. Jeez. Yeah, it's fine. Right, plug in 0 here, just like it does up top. Plug in 0 here, you get a 0 there, but then you got 9 square root of that is 3, times 5 is 15, minus 15 is 0. Okay, we're good. All right. So yeah, there's a lot more that goes into it, but like crash scene analyzers are like people who actually will analyze crash scenes to determine whose fault it is and all that stuff. Usually they work with the police to analyze these accidents. I actually worked with one in my Calc 2 class. She was really interesting and told a lot of random stories about stuff. So she was trying to level up her, or get a math degree and level up her job. All right, so yeah, anyway. If we look at it in terms of like my earlier methods of talking about how to do stuff with, I'm just gonna, I need to stop. I'm gonna get really deep into analysis and it's gonna be terrible. So more or less what we've got is a point down here where the technical zero of this thing is. It climbs up really quickly, goes through zero, and then continues to increase off like this. So there's no real like physical representation of the stuff that's before zero, like in the negative direction. This technically doesn't exist. It's just like sort of a buffer zone for all the stuff that is going to go forward from 0, 0. And it moves forward like this pattern rather than like this pattern which goes up further. It's weird sometimes. All right. Yeah, so anyway, you do seem to only describe roots in terms of their effects uh, as powers. So again, what number when we raise it to the 6th power gets us 500? Again, it's sort of describing it in reverse. This is going to be the same as logs, more or less. So, you know, you've got something that's like y equals 2 to the x. This has an equivalent form of this equation as x equals log base 2 of y, which in this case we're saying right, what exponent on 2 gets me y is kind of the same point here. We're saying like, well, we're trying to find the exponent x given a value y. So again, like, you know, 7 equals 2 to the x. How do we do that? That's saying what exponent are we going to get? That's our x here for on a base of 2. That's going to get me this 7 value that's here. So x equals log base 2 of 7 is going to be the equivalent form, and it allows us to solve this equation. So yeah, I totally... that's also a good question. So... touche. I don't know. So like I've got a couple of different ways to do it. Yeah, how to calculate solve square roots. No, I don't want to do that. Yeah, I mean, that's one way to do it, is just figure out what the approximation of it is. You could try to solve, you could try to go backwards and solve the other equation. Yeah. Ew. Why? Yeah, so that's an interesting point, is like if it's not going to be found immediately, it's not going to be found at all in terms of getting like an exact value. Now, there are of course things like 2.25, which you can take the square root of 2.25 and it's 1.5. Um, and how does that work? Well, the square root of 225 is 15, and it just happens to be that, sorry. So it's not an exception. This is an interesting thing. This is really the square root of 225 divided by 100. So what you've got is the square root of 225 divided by the square root of 100. Square root of 225 is 15. Square root of 100 is 10. So this is going to be 1.5 or 3 halves. Yeah, right. Exactly the same stuff. So if you have it as like a numerical representation, this is one way to do it. If you do it as a fractional representation, it probably makes more sense. Yeah. It all depends on how you're looking at it. Yeah, touche. Right. Yeah, but the second you get a square root of 2 or a square root of 3 in there, you're not going to find it. It's going to have to be an approximation. So yeah, I think probably most. So the answer that I just found in 2 seconds was that it seems that most modern CPUs automatically have like the square root function built in as a native operation, so it's not a problem. However, arg, um, like if you want to build it in, one of the ways that you're going to probably do it is Newton's method, which you said already, right? You've probably seen it before. It happens to uh, like find some sort of approximation, and it gets you. But again, it ends up making like almost circular logic, because you're going to have to take the square root of something that's not nice in order to figure out what another square root is. So like, how's that going to help? In theory, you could also get a calculator to find an approximation, like uh, what's the closest rational pair that are going to get you perfect square divided by perfect square as close to your current value, and then take the square root of that, and it's nice, and then find the next find the next perfect square divided by perfect square that's the closest to what you just found, and then approximate it again. But again, yeah, I wouldn't do that. It's an interesting theory. How's my volume, by the way? Okay, cool. Thank you. I went back and looked at a couple of other videos to try to, edit caption or not captions, edit uh, titles and stuff like that, and I was noticing that it was really quiet. So I don't know if that was just me or what, but yeah, I think mostly just because there aren't any good like applications for it that can tell you, real quick at a glance. There are some that are like, what is it? Height of a tree versus its age or something like that is, I think, technically a square root function. Um, so as a tree starts growing out, it also needs to grow into the ground to be able to really grab on to the ground and not fall over in the slightest breeze. So there are there are things to describe which are similar to that, which might, I don't know, might help you. Yeah, ew, no, you can't do that. So there are a couple of different ways. With like basic algebra, I usually say like when you wanted to take, it's like, I don't know, 8 to the third or something like that, right? Yeah, you could do that. Right. Yeah, so that's one way to do it. Um, Another thing that I usually say is like, how many 3x squared y? How many z's are in this equation? Right? There aren't any. So then you'd say, okay, well, how many y's are there? There's one. How many x's are there? There's two. How many 3's are there? There's one. So how many z's are there? Well, there aren't any. But instead of saying there aren't any, you could say there are 0 z's, in the same way that there is one y, two x's, and one 3. Yeah, and then you can keep tagging on whatever you want here. Yeah, any variable you want. It's got a 0 exponent on it. Any, 2's. That's not a prime number. 101 to the 0, whatever you want. There aren't any. So, yeah, 3x squared y to the first times 1. So I mean, basically, you're looking at induction, the way that you're visualizing this. Is that like you're looking at it forward and saying if you keep counting the number of a's that you have multiplied together, that's going to be your b. And then when you walk backwards and have 0, that's when you have nothing there. Ah, okay. I also see. Yeah. So, that's the other reason. Is that our operation, multiplication, has to have two inputs. And if one of them is the multiplicative identity, it always just comes back with the other thing. That might be getting a little abstract, but... Right? And we come back to the root of the problem. Or the problem of the root. Whichever way you want to state that. Okay. No, that's not right. Whoops. No. It's not multiplied by. Right, it's what do you take this raised to. So you'd have to get a 1/2 here in order to get x to the first back. Yeah, I'm trying to think of something might be a bit better, but there we go. I mean, whatever we want, Matthew, it's fine. Trying to see if there's another another way to talk about it specifically from like the abstract algebra perspective, because that might be able to come up with something that looks at least a little bit nicer. Um, yeah, they're all just basically talking about how to reverse polynomials. I mean, it's like looking at it from that particular perspective. Of course, that's not really what you want. C, D. You got all sorts of polynomials, rational functions, instructions of extension fields. Um, so multiplication I usually think of as repeated addition, and division you can actually think of as repeated subtraction. It's like you're just subtracting off that many things, and then the quotient is how many things you, or how many times you're going to subtract it off. How many groups are you going to create as you pull that thing off each time? Yeah, I know. And then the remainder is how many are left over at the end. So, yeah. Well, it depends on your perspective. So, I mean, you've got, you know, I mean, I guess the biggest problem with it would be like you're thinking of it in terms of, if you're thinking of it in terms of repeated multiplication, then you're looking at it in terms of integer multiplication, really. Um, then if you use decimal, okay. So how do you prefer talking about multiplication? You got documentation on that somewhere? Or is it like something that you developed and it just works great? Because I mean, that's fine too. I don't think I see it just because I'm kind of stuck in my little mode of what I've got going on. So basically, is this what you're looking at? Taking each of the 5 things that are here, replacing them each with 4. I mean, it's commutative, so therefore right, multiplication works on a commutative basis in well for real numbers, so we're okay with either way you do this. But yeah, well, again, that depends on your perspective. If you're just adding all the groups up, then no, it doesn't. But yeah, I understand. Which is also interesting if you try to say like, let's do this with matrices, because then potentially things don't, they aren't commutative necessarily. Of course, I don't know how matrices plays into any of this, but hello, Grey Wolf. Okay, so not really. So it isn't all that hard. It's just Matthew and I are trying to discuss a different way of visualizing what's going on with multiplication, and I'm I'm old, so I just kind of plod along in my typical way, um, and he's trying to get me to think outside of. Hmm. So you're also technically distributing then. You're saying that this is like each of the 5 things here are splitting up into 4 things, essentially. The 5 is then going to be 1 plus 1 plus 1 plus 1 plus 1. So therefore, it's going to be 4 plus 4 plus 4 plus 4 plus 4. You're going to hate me for that. Yeah, Grey Wolf, if you have a question on it, feel free to drop that in chat, and I will... we can get right to it. There are so many different proofs of the Pythagorean theorem. Oh, man. I tend to like that one, yeah. Yeah, I tend to like that one. Is that the one that Garfield came up with? That's a slightly different one. Anyway. So, yeah, Grey Wolf, like I said, feel free to plop any questions in chat that you might have. If it is going to be a particular example, I might decide to change it a little bit just because I don't want to do people's homework for them, no offense. But we'll definitely talk about it. So yeah, James A. Garfield, who was the president of the United States back in 18, whatever it was, published in 1876 in the New England Journal of Education a particular showing of how the Pythagorean theorem worked. So I think his is probably the one you're talking about, but he did a half of a square rather than the full square, which is probably the one you've seen before. It's like this is a. Oops. This is fine. Yeah. So the area of a trapezoid is going to be this thing, so that's a plus b parentheses squared over 2, and that's equal to this area here, which is going to be a times b plus 1/2 c squared. Multiply everything by 2, it's going to be a plus b parentheses squared is equal to 2ab plus c squared. Multiply this out, that's a squared plus 2ab plus b squared plus 2ab plus c squared. Take out 2ab from both sides. Yeah. I was like, oh, okay. Got kind of a genius over there. So, yeah. I'll take the compliment, but yeah, I'll take the compliment, but at the same time, I'm not the originator of this thing. This is again James A. Garfield from the former president of the United States and one of the assassinated presidents from the 1800s. Was the one who came up with this. Again, published in New England Journal of Education. Ironically, April 1st of 1876. So the almost centennial edition of, yeah, New England Journal of Education. So yeah, there is also, and you know, don't get me wrong on this. I wasn't doing this off the top of my head either. Once I got the picture down, I could do it just because I know all the formulas and that stuff. But yeah, this is not particularly difficult once you know what the formulas are. Yeah, Matthew, there is also another really good one that was done. I don't have time to to go into it because it is insane. But it's basically using Euclidean geometry to solve all of it. So, that's awful. All right, whatever. It's cool. If you want, you can draw it in paint and make a much better example. I don't know about no algebra, but this is awful. So no, not exactly fit into. Um, this uses the same Euclidean geometry. Sorry, yeah, Euclidean geometry that we did in like I don't know. For me, it was 10th grade or ninth grade. For me, it was ninth grade. I don't know when you all do, and it's different for every state. So I mean, whatever. Um, but basically, let's see. That one. Yes. So it uses that kind of Euclidean geometry. So the official proof type that. All right. Hang on. My diagram's sideways. So we're going to use, let's see, this one goes from here to here. And this one goes from here to here. And if this is the right angle, then also dropping an altitude down splits this into two pieces. And you can add there it is. You can find that this area here is equivalent to this area here. And then you can find that this area here is equivalent to this area here. So then if this one is a, then therefore this is going to be a squared. If this one is b, then this one is therefore going to be b squared. And so this is b squared, this is a squared. And then combine them to get the areas. Yeah. So I mean, you have to go into a little bit more detail to truly get the equivalents to work out. I cannot do this one off the top of my head. I have to actually look at like the progression to do it, but it would be an excellent exercise. All right, so basically if we want to look at how to do Pythagorean theorem stuff for Grey Wolf, for instance, if you lock a, say, 8-foot ladder on the ground, yeah, I got you. And it is a total of 3 feet away from your house. And let's suppose that your house is well built. This does have a right angle to the ground, or at least to the straight line distance that is out where your ladder is anchored. Then you want to know, how high up can we reach? So this is probably much more what you're used to. Yep. So if we're looking at this, this is going to be like a squared plus b squared equals c squared. And you're right, the legs of the triangle are going to be the shorter sides are 3 and are unknown. And the longest side is going to be our 8, so that's our c. And actually here, it doesn't even matter which one you use. It could be A, it could be B. So, if you don't mind me asking, where'd you come from? So, did you just come off the Twitch page, or did you come off of Homework Help, or? No. Some people prefer to keep the variable as the first one and then leave the second one as your number. It doesn't really matter, as long as you're showing your work here to. So, yeah, we end up with 9 plus our b squared is going to be equal to 64. And my personal preference, I much prefer to subtract off from both sides. This way, I'm showing that -9 is equal to -9, and that is causing us to, awesome, well, welcome. All right, so here we can add our two equations together. And when you add a 9 and a -9, you get 0. And then our b squared here is going to be left over, plus 0, doesn't do anything there. And then that equals our 64 minus 9 is going to be 55. Yeah, I mean, why else would anyone look up math streams? It would have to be out of boredom. Anyway, so here, then the operation to undo this is going to be to square root. And we're going to get the absolute value of b is equal to the square root of 55, which in this context, we can only want the positive version of this. So b is going to be equal to only the square root of 55, which is approximately 7 and something. All right, 7.4161998, etc. It keeps going from there. I mean, fair enough. Yeah, being able to talk math with just somebody is much more, certainly much more engaging than trying to do it yourself, or to just go online and try to look it up on a static video. Because I mean, I've also got videos on my Nsimflex Pachinko YouTube channel, but again, it's the same sort of thing. It's like I'm just kind of talking at you instead of interacting with you. This is much more interesting for everybody. It's also another reason that I haven't done any of those videos in such a long time. Oh. All right, and then realistically, what kind of thing are we going to want here? It's probably going to be 7.4 feet. You know, let's be honest. Our approximations for this are only going to be accurate to probably one decimal place, maybe two for, feet. If it were centimeters, again, probably just one decimal place. Uh, Two would seem unlikely unless you're doing something very high precision. Oh man. So fractions really came about because of what we were talking about earlier, like the number of groups to split things into, or the number of subtractions you're trying to make. Again, depending on your context. If you're trying to split 8 things 3 ways, then that wasn't what you meant, huh? Yeah. So, I mean, I think that radicals really just came about in the same way that actually fractions did from multiplication. It's just you're trying to undo an operation. So, the physical operation in terms of multiplication and division is much more obvious. Where you're saying, like, I'm trying to undo this multiplication, I need to divide, and therefore I'm going to come up with these fractions, and here's the big process in order to do it. And then when people started looking into it a little bit deeper, it became yeah. So that would be the progression in that particular instance. So I mean also decimals technically. But the really what you're talking about is algebraic numbers. So like all of the combinations of rational and irrational numbers are going to I shouldn't say all irrational. The all the combinations of real and radical irrationals are going to create um, the set of algebraic numbers. So algebraic numbers are going to be the, and this is really the problem. The set of algebraic numbers are going to be the uh, set of all numbers which are solutions to polynomials. Yep. So I think the problem, yeah, I think the problem is that we're looking at this in terms of like, well, here are your natural numbers, which are going to be all of the things that you just count with. So, 1, 2, 3, 4, 5, etc. And then outside of here, you're going to get your integers, which are going to be the um, right. So, sorry. Your natural numbers are closed under addition and multiplication, but then, yeah, when you start saying, well, what's the inverse of all this stuff? Now you have to include all this. And then when you say, what's the inverse of multiplication? That's when you have to include the rationals. Then when you try to get the rationals, you're like, okay, well, what now? Which? So, closed under exponents. So, naturals are closed under exponents. Yeah, naturals are closed under exponentiation because you can raise them to that same power or any other power, and you get another integer. Yeah, or you get another rational number. It's when you expand out to integers that you say, well, if I have a negative exponent, now that's going to get me a rational, a rational number. So I need to include that. But then when you say, what about fractional powers? Fractional powers are what are the impetus to cause us to get the algebraic numbers. Mm. No, not division. Sorry. Just subtraction. So subtraction allows us to get the integers from here. Integers using division is going to get us back out here to rationals. Rationals using exponentiation is going to have to get us algebraic numbers. Again, natural numbers are going to be closed. Integers raised is going to also have to get you rationals. Yeah. They'll definitely get all sorts of messy and things like that. So then yeah, I mean, you could even argue that exponentiation here with fractionals. No, wait. Right. Exponentials here with fractions are what are going to get you the complex numbers on the outside in the first place. So it depends. Algebraic are going to be the solution, are solutions to some polynomial equation. Which also means that, like, some polynomial equation is going to mean that this also involves, like, your coefficients have to be rational numbers. Technically, that means that it's equivalent to having them all be integers. But when you do, yeah, when you're just doing, like, an integer or, rational, when you're doing a rational number plus any irrational number outside, then it just ends up being an irrational number of some kind. We don't know what it is. It might be algebraic, but that's only if it started as an algebraic number in the first place, if your irrational number is algebraic. Because then outside of algebraic, you've got the transcendental, which are going to be things like pi and e and anything that looks like 0.10100100001, stuff like this. Things that have like generative patterns, but you can't actually come up with an algebraic number to describe it. So most numbers are actually in the transcendental category. So if you like randomly generated a whole bunch of digits, that's going to be a transcendental number if it goes on forever. If it stops at any point, it's rational automatically. if it's going to go on forever and it happens to be exactly a solution to a polynomial equation, which again, if it goes on forever and you did this literally random numbers, it's not going to be. Might be close to some, but it's not going to be an algebraic number. It's going to be transcendental. And that's also another weird thing, is like, okay, you're telling me if I generate an infinitely long string of digits, then it's just going to be a transcendental number? And I'm like, yes, absolutely. 100%. So yeah, that's an interesting problem. And this actually goes into the history of math. So Georg Cantor was a German mathematician who was alive in the 1850s-ish. So actually sometime around roughly the same time as James A. Garfield, interestingly enough. And he was working on a new classification system, which is this thing here. This is exactly what I'm doing. And it was eventually turned into what's called set theory. And Cantor was like, okay, well, let's try to describe like how big these sets are, because I mean clearly the integers are larger than the natural numbers, right? I mean clearly you have the natural numbers are actually a subset of the integers, and therefore since the right, I mean obviously, right? It's literally a subset, so therefore it should be smaller. Right. But the thing is that Cantor went through this and he said, well, this is kind of interesting because if I go through this and I say that I have my list of natural numbers, so 1, 2, 3, 4, 5, I'm just going to list a few, right? And then I'm just going to keep going on forever beyond here. And I take my integers and I go through and I say, well, this is 0, 1, 2, 3, 4. Okay, well, clearly I'm not going to get to any of the negative numbers, so this is going to be, integers are going to be bigger. But then he said, well, wait a sec. If instead of doing that, I say 0, then 1, then -1, then 2, and then -2, and then 3, and then -3, all of my integers will now be in a one-to-one correspondence with all of Have you seen this before? Yeah. All of my integers will be in a one-to-one correspondence with all of my natural numbers eventually. So again, have you seen this before? So it's not that literally, yeah. So it's not literally that they have the same number of things because it's infinitely large and you can't do that. It's right. You can't literally say that they are exactly the same size because there are an infinite number of objects, and infinity is a really weird concept to mess around with. But these sets are of the same order, really is what should be is how it should be described. So the natural numbers and the integers are of the same order. And he termed it, or at least it has been termed, countably infinite. Which is whoa, I have to draw that now. Okay. So this particular order is called Aleph Knot, and right, since it is a technically a proper subset, it is bigger in that it has more elements, but but then you could say, well, I can put it in a one-to-one correspondence. So they are both countably infinite. They are of the same order, even though literally one of them has more things. Yeah. So this Aleph Knot and the symbol given here, usually, actually, I just looked it up. It's more like that, but yeah, I'm just not good. It's Hebrew. I don't write Hebrew. I don't know Hebrew. It's cool. Right. So essentially, it is a smaller infinity allegedly. So then Cantor said, okay, well, clearly the rational numbers being stuff that is a over b, where a and b both belong to the integers, has to then be much, much bigger than the integers or the naturals, because it's an infinite number of things in between any two of these, right? If I pick just the distance between 0 and 1, there are an infinite number of rationals that belong between 0 and 1. So, like, it has to be bigger, right? And so Cantor went through this and he was like, well, actually, if we draw this out as yeah, as two-dimensional figure, this is 1, 2, 3, 4, 5 along our A axis here. 1, 2, 3, 4, 5 along our B axis here. 3, 2, 1. All right, we're going to start at 0, 1, which is going to be 0 divided by 1. So 0 over 1 is going to be the first one. And then if we go to 1 over 1, and then we go to 0 over 2, and then we go to 0 over 3, 1 over 2. 2 over 1. 3 over 1. 2 over 2. That's 1 over 3. And 0 over 4. And then 0 over 5. I think you can see where this is going. 1 over 4, 2 over 3, 3 over 2, 4 over 1. Yes, you can list out every rational number eventually in this long string as you go out. Well, no. But that's also actually technically part of the point. So it turned out with this, since rational numbers can be placed in a linear formation, can be placed in a one-to-one correspondence with naturals. So this also meant that the rationals are going to belong to Aleph naught as well. Oh man. So this means that the rationals are going to belong to the same Aleph naught, just the same as the integers. There are like an infinite number more of them, but at the same time you say, well, they can be placed in a one-to-one correspondence, so therefore again, it is a proper subset, or rather the integers are a proper subset of the rationals, so of course there are more elements, but at the same time so this is actually one of the things that caused Georg Cantor to be hospitalized in his many years of tenure, is that he basically drove himself insane trying to think about infinities. This was the cutting edge of mathematical research at the time. Hospitalized in the sense that he went to a sanatorium and decided that he needed a break. Sanatorium being a, rich person's mental institution. So he institutionalized himself for sometimes months, sometimes I can't remember what the longest stint was, but yeah, months at a time. Let himself kind of take his mind off the hook for a while and no longer need to think about mathematics, the very, very difficult cutting edge research that he was doing. And eventually he kind of weaned himself back into it and, okay, feeling a little better. It was then that he went further and decided to try mapping to the reals, like all real numbers. And so he ended up coming up with a proof for real numbers that was, okay, let's come up with some sort of, yeah, brain's got to soak it in. Let's come up with a decimal approximation. So all numbers between 0 and 1, and we're only going to use binary. This is not what he did, but let's think of this as only doing a binary representation. So 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, whatever, right? This is infinitely long. And 0.1100011100010 0.1, nope, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, 1, 0.0101. That's good enough. So what I'm going to do is I'm going to state that I am going to create a list. This list complete list of all binary representations let's call them R, that are between 0 and 1. Right? So let's pretend that we can do this. Right? It's infinitely long. And there is an infinite number of these things which will go on forever. It has every single possible binary representation on it. So I cannot possibly add another element. Correct? Seems like it. But if I take, now this is going to start with 0 point, obviously, because it's between 0 and 1. If I take the first element of the first number and I change it, make a 1, and put it down at the bottom. If I take the second element of the second number and change it, and the third element of the third item and change it, and the fourth element of the fourth item and change it, and the fifth element of the fifth item and change it, and continue this pattern, I'm going to come up with a new number that is unique from the first, unique from the second, unique from the third, etc., unique from the nth position. So no matter what that list had, this will have to be a new number. Which breaks the whole thing that we just talked about here. So therefore, this can't be a complete list. Therefore, it can't be countable. Therefore, the reals must be distinct from Aleph Knot group. So the reals must belong to some group. Jeez. Must belong to this new group, we'll call them Aleph 1, which are going to be uncountably infinite. Yep. So there is also a continuum hypothesis, which came up way after Cantor, which stated that here there exists a group between. It's just going to be different every time that I draw it, so it's fine. Between Aleph 1. Oh man. Don't give up my day job. Aleph Knot and Aleph 1. So the continuum hypothesis says there is some sort of infinity that belongs between the countable infinity of these ones, right? The rationals, integers, and counting numbers, and this kind over here, which are from the reals. So, continuum hypothesis was one of the nope. Hilbert's problems, I think. So David Hilbert from the 1900s wanted to know, like, okay, let's make sure that we have, like, let's come up with, he called a meeting of, like, all the great mathematicians and said, okay, let's set out all the problems that exist in mathematics that we know so far. And, like, what are the cutting edge research things? What are the questions that we absolutely have to know the answers to, because we're in the 20th century, for Christ's sake. We should be able to figure this stuff out. So it's not missing numbers, it's missing groups, or like missing a classification of numbers. So like, are the algebraic numbers falling in the do the algebraic numbers fall here or do they fall here? Right? Are they in Aleph naught or are they in Aleph 1 or are they in something in between? And so I think there's a way to prove the algebra. I've never actually seen the algebraic numbers get proved into one or the other, but like, let's figure out, right? Not really. So algebraic numbers are just a generalization of sort of the rational numbers, saying like, okay, we're going to take rational numbers and we're going to say, what other like larger group do we get out of this? Well, solutions to polynomials are going to be the next size up. You could go all the way out to transcendental and say, oh, well, roots and like all irrationals are part of this group. And then somebody said, well, yeah, technically, but then those irrational numbers are split into two groups. You've got algebraic and non-algebraic, or transcendental. So if we go back up here. Right, so it was just that all of this was... At some point, somebody just called all of this irrational. And then somebody said, well, let's split those because actually we can break it up into two different groups. I mean, she is perfect. Right, that and the matrix, right? So you've got these irrational numbers, which are both of these groups put together, and then somebody was like, well, algebraic numbers really are separated from that, so we could do, what are solutions to polynomials? And so they came up with algebraic specifically. And then transcendentals, again, are some sort of patterned numbers, or potentially unpatterned numbers, like pi. This transcendental number here, I was just adding a 0 each time between each one. So there are no zeros here. There's 1, there's 2, there's 3, there's 4, there's 5. We just keep going with this forever. Right. Or, well, pi can't be defined with a finite set of rules, probably. Yeah. Actually, we do have... Yeah, there is an infinite sum. Yeah, maybe. These are the only ones that I've like technically classified in my travels with all of these things here. So like really, I think the easiest way to describe transcendental numbers in terms of this stuff is you're going to need an infinite sum. So like this one here is an infinite sum where you're going to have like 1/10 raised to some pattern. And this one isn't even going to necessarily do that. Huh. Because it changes every time, so it's not. I guess technically that might be like a k-squared or something like that. Anyway, it's not the point. Or 2 to the k. Oh, man. That'd be so evil. But e is taking the limit as n goes to infinity of 1 plus 1 over n to the n. Pi ends up being an infinite sum exactly. Yeah. Yeah, maybe I'll have to get myself into a combat zone in Elite as well and just decompress for a while. But at any rate, thank you so much for coming. I'm going to send out. Where are we? Nice. Alright, we got Boss Lady B doing Elite Dangerous. Dev the Devastator doing Astroneer. Lynn Marley doing Phasmophobia. Oh no, I missed Jason Charles Miller. He's doing math too long. Alright, I think we're probably going to be raiding Dev tonight because haven't done his stream in a little while. So have a good night, everybody. Gonna head out to Dev the Devastator, who is doing Astroneer, and hope to see you again. I will be doing another gaming type stream on Friday. Probably going for, what am I doing again? Noita, again, get some more stuff in the encyclopedia there. I think probably my time in Noita is coming to a close, but we'll see how it goes. And after that, going to do Control again. After that, I think I want to start doing an actual speedrunning attempt at Astroneer because I'm starting to get an itch for that again. And and probably going for eventually start coming back to Elite Dangerous. I might just do an Elite Night, and at some point over the summer I might do a second math stream night. It depends on demand. So good luck to you out there. I'll see you later. Have a good night.